Hey folks, we're about to start another episode of Ask Us Anything about electrochemistry. But before we begin, because we have some extra time, there are a few things I'd like to go over first. While we're waiting for the live stream to start, type your question into the chat. The sooner we get your question, the sooner we'll be able to answer it when the live stream starts. We usually try to answer questions in the order that we receive them, but it's definitely possible that we get so many questions that when your question comes up, we're out of time. If you are a Tier 1 or a Tier 2 YouTube member, you do get priority in us answering your question. You also have the opportunity to join us on the stream to either share slides or talk to us in person about your specific electrochemistry research questions. If you are a Tier 1 or Tier 2 member on our YouTube channel, you will find in the community post the link and password to join us on our broadcasting platform. We get a lot of questions about electrochemistry, whether it's through our YouTube comments, webinars, email, phone conversations. We get lots of questions from people about electrochemistry. And sometimes responding to a YouTube comment or trying to describe a cyclic voltammogram over the phone isn't always the easiest way to teach or describe electrochemistry. That's why we created this live stream. In the Ask Us Anything About Electrochemistry live stream, you can ask us any questions you have about electrochemistry, and we can use better tools and take more time to describe some of these electrochemical processes to help you with your research and understanding of electrochemistry. Now, in our time of doing this live stream, we've observed that if you ask a very, very specific question, we might not be able to answer it. It'll be a little bit too specific for us. On the other side, if you ask a very broad question and you're interested in just a very broad understanding of cyclic voltammetry, we have separate tools, we have other resources to help you. So we do have a YouTube video on cyclic voltammetry, an introduction to the subject. And if you're interested in more of a long-form course on, say, electrochemical impedance spectroscopy, we have a 5-part EIS webinar series for our Tier 2 YouTube members that you can access at any time. Now, if you weren't aware, Pine Research Instrumentation is a company that produces a wide array of high-quality electrochemical research equipment, from potentiostats to electrodes, electrochemical rotators, cells, different types of accessories. Pine Research has been supporting electrochemistry research and teaching for decades. Recently, we have developed new electrochemical simulation software called Aftermath Live. Aftermath Live is an online streaming platform where you can simulate popular electrochemical techniques like cyclic voltammetry. It's a powerful research tool, as you might simulate a cyclic voltammogram to support an electrochemical mechanism for your redox reaction that you're studying. But Aftermath Live and cyclic voltammetry simulation is also a very powerful tool when it comes to just learning electrochemistry. In fact, in previous episodes of the live stream, we have used Aftermath Live and our simulation software to answer some of the questions that you have. If you are watching this on YouTube, you can get a 10% discount on your first month of the basic and research editions of Aftermath Live by using the coupon code PINEYouTube10 when you're at checkout. Aftermath Live is a powerful tool and you can cancel your subscription at any time. Go to aftermathlive.com to check it out. Link is in the description below. Our live streams are normally on Fridays from 1 to 3 p.m. They normally last about 2 hours, sometimes a little bit more, sometimes a little bit less. If you miss the live stream, you'll always be able to watch it on our YouTube channel, and in the description we put timestamps for every question that was asked. This way you can look through the description and find the questions that are most relevant to your research and then watch those at your leisure. Also, we apologize in advance if we mispronounce your name. If on a YouTube channel you can put anything you want as a name. It could be a Pokemon, it could be a string of numbers. But if we call you out and we accidentally mispronounce your name, we apologize in advance. Lastly, please do not spam the chat. We've had numerous instances of people either talking about inappropriate things or constantly filling the chat up with some kind of spam. We will remove you if you do that. Let's keep the chat very clean and just talk about electrochemistry. Sometimes it takes a while before we're able to answer your question. So if you keep typing your question into the chat and spam the chat, then we will remove you from the chat. But if it's been a while and we may have forgotten about your question, one message as a gentle reminder is all that's required. All right, I think that's all of the housekeeping things. Now, let's start the live stream.
All right.
All of a sudden, the music stopped.
That's right.
It was like, I was expecting it to fade gracefully, and then it just died.
And it's just like, boom, it's done.
It's over.
All right.
It's anticlimactic. Hello, everyone.
Hello, everybody. Good to, well, we're not seeing them.
We're not seeing anybody.
We're not seeing anybody. We're seeing the camera.
I'm seeing myself and you
Yeah.
on my own computer screen.
That's right.
It's not very exciting. Hey, I have a really important update for you, Alex. Are you ready for this?
Yeah.
We have a website.
Yes.
I know this is very shocking news in 2026, but we work for a company, and that company has a website.
Yes.
Let me show you. I'll prove it to you. And I know you don't believe me. I'm going to prove it. Boom, right here. That is a website. It's a website for our company, Pine Research.
Yes.
You might ask yourself, why am I showing you a website? Well, other than the fact that it's the most beautiful website you've ever seen, we have somewhat of an announcement to make. I suppose it hasn't been fully detailed out, but we are on this live stream going to be taking your questions from our website. So you may be familiar, for instance, with contacting us on our website. You can send us a message. So a lot of people have done this. Of course, a lot of people do this every day, every week. You submit your message, and you know, general inquiry or whatever it is. You can see that it'll fill in your information. Then you put, you know, answer my question now. Right. Oops. Answer my question now. There you go. So we will be moving this live stream to try to take advantage of this, because we get questions from you guys and every week, and we do this Ask Us Anything about electrochemistry live stream. And sometimes it's like we reach, you know, the end, or we reach our time limit, or people maybe didn't get to get their question answered when they wanted to. So what we're going to do is start using our website. Now, it'll probably be slightly more fancy kind of an interface that we'll have to wait on that to announce. But what we want to do is encourage you guys to submit your questions on our website that you want answered, just any general Ask Us Anything about electrochemistry questions. And we're going to try to do priority to those who submit their question on our website. And you can even put like your YouTube handle, like, oh, well, I'm this on YouTube, but I actually have a real name as well, not just, you know, a mishmash of letters and numbers. And so you can tell us what your name is and where you go to school, or what where you're studying, and put your question. And we're going to give priority to those and try to answer those in the first like hour of this live stream. And we'll try to try to be able to, you know, do that. And so we'll still answer questions live, as we always do every week. But we're gonna start, you know, seeing if those who are willing to have a question that you want to, you know, type out, and you might be able to type it out maybe more with more detail on our website.
Yeah. There's some character limitations on YouTube. You have to end up having a bunch of things,
and you could submit like a file or a CV.
Submit a file,
on
picture.
our website.
It'll be very helpful, and I think it's always more clear, and it just will help. I know a lot of people just sometimes can't watch the live stream when it's live, and they have to do things afterwards. Mm-hmm. And sometimes we'll say like, oh yeah, just send us an email or something like that. And sometimes these things get lost. They don't end up getting processed properly, so that we can very easily answer the question, or we forget, or what have you. So this is providing a little bit more structure to the nature of the questions and our ability to answer them by going through the website. So more details will be coming in the future, but for now, we're going to encourage you to also, yes, type it into YouTube, type it into LinkedIn. But if you can't make it and you want your question answered, you really want to make sure that your question's answered, start using the website.
Yes.
Yes.
We're gonna have more information with that, but for now, we'll just move on. And it looks like we do have a question from Miraj. Says, what exactly is the role of exchange current density in the Tafel slope analysis? Exchange current density. Also, Tafel slope is somewhere calculated from potential versus log current density, and mostly it is over potential versus log of current. It sounds like you're asking if there's a difference between plotting it versus like potential or over potential. Do you want to talk about exchange current density? It's your favorite thing in the whole world.
My favorite subject in the world. Yeah. Also, I'm gonna
pull. I have some Tafel data. I'm pulling it up.
Also, there's something a little. The format looks a little weird with how the ticker is and the person's name is on the bottom, and it's like bothering me a little bit. So I'm gonna.
You do that while I find.
I'm gonna hide. I just want to hide.
Is it the ticker? Why is usually the name's on top? Why is it on the bottom?
Yeah. I don't know.
That's weird.
Yeah. So
unhide and hide the question. I don't know.
Yeah. So I'm gonna unhide this. We can. It's okay right now that the question comes up front with the name in the bottom. That's okay. It's just weird with the ticker on top.
Yeah, it's bizarre.
But the role of exchange current density. So the exchange current density is it's usually defined as like I naught. Actually, exchange current density has always been a somewhat interesting kind of concept because the exchange current density is a measure really of how easy is the electron transfer. So reactions that have a very large exchange current density just means, oh, for a given amount of potential, I can really get more current to flow into the system. It's easy for the electron transfer to occur. And similarly, the if you have a very low exchange current density, it means I have to apply a lot more potential before I'm able to get more current to flow. So it's a measure of the ease of electron transfer. The reason why I personally don't like exchange current density that much is because exchange current density is really analogous to the rate constant, right? The rate constant is a measure of how easy is the electron transfer to occur. So, but exchange current density is just, if we take the current and we divide it by the area of the electrode, we're able to calculate an exchange current density. Or if we're measuring in our Tafel plot the current or the log of the current density versus the overpotential, we can talk about things in terms of exchange current densities instead of rate constants, and there's less division and normalization, sort of say, or there's less calculations you have to make to get a rate constant. But the rate constant would be independent of the area of the electrode, sort of say. So
I can answer the other part of it. I have
sure
Tafel stuff now.
Yeah,
I just wanted you to talk about it because it's fun to make you talk about things you hate.
Yeah, that's right.
Because I have to do it, so you have to do it too.
Because you can just talk about the rate constant. That's all. That's why I don't like it. It's just like, why exchange? Just talk about the rate constant.
I also hate the exchange current density, just not as much as you do. But I hate it because I think it's like weird to talk about a rate constant in terms of a current, because the rate constant succinctly describes the speed of the reaction.
Yeah.
Right. The current makes it sound like that's how much current is passing. That's not the case. It's like it's like we're using it as a constant, but it's like, well, but current is for how many electrons are moving, and that's not what it's telling you. But it's like, well, then why is it used as current? It kind of like, it doesn't make sense.
Yeah.
I agree with you. I just like to tease you because it doesn't bother me as much as it's like what a potential should I do impedance that bothers me. But
yeah.
Okay. So the second part of your question, the short answer is it doesn't matter. Okay. So if you plot potential or over potential versus log I, it does not make a difference. And the reason is that it's a slope. Okay. So when you have a slope, it's the change in Y over the change in X. The Y is potential. Okay. Or over potential. The only thing that changing overpotential to potential or vice versa does is it shifts the axis. It's the same thing as changing your reference electrode. It doesn't actually matter if you're taking a slope, because I'm looking for the change. It's how much it changes. So the overpotential is how far. Now, let me clarify. Technically speaking, overpotential is the correct thing to plot, because that's what's in the Butler-Volmer equation.
Mhm.
Technically, overpotential is part of it, but you can just plot potential. It doesn't matter. I'll prove it to you. Okay. Let me share our
Yep.
software here. I have some Tafel data. So I already imported this in here. So you can see this is potential on the y-axis. Okay. And there's no unit here because it's the log of current, right? On the x-axis. Okay. When you take the log of a unit, it's decades, right? This is like 10 to the minus 5, 10 to the minus 4, 10, whatever. Hopefully you get it, right? And so when I take the slope, it depends where I take the slope, what the value will be. But let's say I've identified this as my kinetic region. I think I get about 90. It depends where I take it. It's that's about 120. There you go. That's a nice. That's my 119, 120. Okay, everything's all happy. Great. Okay. 120 millivolts per decade. I've got my Tafel slope over here. This is my kinetic region, blah, blah. Everybody's happy. Okay. This is plotted as potential. Let's say I say to myself, well, I'm supposed to do over potential. I'm going to make a copy of this plot so I can play with it. Okay. Let me just get rid of the baseline tool real quick. So here's my data. So what I'm going to do, I know you probably can't see this. I'm going to do a quick operation on it, but what I'm going to do, again, I know you can't see the pop-up, but let's say, see this y-axis potential? Let's say I want to transform this, so to speak, to overpotential. So if, for example, the E0 of whatever I'm studying, so you see that the y-axis here goes from like 0 down to minus 300 or whatever the heck the numbers are, right? But let's say the E0 was 200 millivolts, right? Positive 200 millivolts or whatever, right? So if I'm at 0, I'm at minus 200 over potential, you might say, right? So what I have to do is I have to subtract 200 millivolts from the y-axis data, and that will transform it, so to speak, to over potential. So all I'm going to do right now, again, I know you can't see the dialog box, but I'm basically taking away 200 millivolts from every y-axis data point. So I made this blue line. It kept the red line so you can see that. All I've done is I've moved. So this right here, this blue line, I'll actually even name it. This trace, the red one, this is potential. Okay. And so all I've done is I've said, oh, my E0 is 200. So this is over potential. So now, technically speaking, the blue plot I've correctly plotted based on the convention over potential against log of I, right? But look at what the slope is. Now I have to pick the right range. It's, it depends where I pick for a range, right? Same. It's exactly the same because it's a slope, right? It's the change in Y over the change in X. So I can get the exact same slope regardless of what my y-axis is as potential or over potential. Now again, it depends on, I don't have
The
these
exact
dots in the exact
the exact
same
dot
place.
points.
Yeah. If I take it in the exact, I'd have to make sure these are close enough. You get the idea, hopefully. The slope is the same. Now the intercept is different, but I don't care about the intercept in this case. Now, if I did care about the intercept, I think you can get another constant if I'm remembering, and most people only care about the Tafel slope. There's something you get, maybe it's the exchange current density, it might be. While we're on the topic. Most people really just care about the Tafel slope. And so to that point, which is part of your question, it doesn't matter what you plot specifically for the potential, over potential or regular potential, because it's a slope. If we were looking at it properly, we would use over potential based on the definition of the Butler-Volmer equation and the Tafel equation. But strictly speaking, for the calculation, it makes no difference. So if you're worried about, well, which potential did I use? Do not worry. It doesn't make any difference because the slope takes into account the change. And going from 0 to minus 2 or minus 2 to minus 4, 100 millivolts, right? Is the same change. It's 200 millivolts of change, right? So so it doesn't matter where I start and where I end. So hopefully that kind of answers your question about the Tafel slope.
Yeah, no, I think that's a great explanation. Great explanation. Next question. Does it make a difference when we run EIS, CV, and DPV in some sequence while electrochemical characterization? Sometimes, and I think that the nature of the question is really, does the act of performing the technique change your substrate in some kind of way where the results would be different? Um, and that answer is in many ways it depends. Generally speaking, I'll say for EIS, EIS usually does a very small perturbation to the electrochemical system. So oftentimes it doesn't matter when you do EIS. You could do EIS before or after. It doesn't change the system where you would get different results for, say, your cyclic. Like if you did a cyclic voltammetry experiment before doing EIS and after EIS, you'd probably get the same CV data no matter what, because EIS doesn't perturb the electrochemical system enough to create some kind of problem. But when you do techniques like CV and DPV, both of these are actively changing the potential of your system, usually over a fairly large or wide range. You could be, you're doing an oxidation reaction, you're doing a reduction reaction, you're doing various charging of the electrochemical double layer or electrical double layer. And if you run EIS, do CV, and then run EIS again, you may have changed your surface or your system a little bit. You may have irreversible absorption of your molecule on the surface, and that did something to your system where the EIS has changed. So generally speaking, depending on the system, if the system is perfectly reversible and stuff like that, then it wouldn't matter. But it's rarely the case. But generally speaking, with EIS, I don't think it really matters so much because it doesn't perturb the system as much. But CV and DPV have a much higher chance of the action changing the system because they're much larger perturbations, and your EIS before and after DPV may look very different because DPV or CV changed the system in some way. So that's my take on the question. Hopefully, hopefully that answers it. If you have further questions about how in what order should you do things based on this, let us know.
There's a question next. Unfortunately, we're not really going to be able to help you here. This person says, I would like to kindly ask if you could show me how to plot CV, GCD, and EIS data from Metrum into Origin, as I'm currently encountering some challenges. I was using EC Lab before. Unfortunately, we can't.
Yeah.
Metrum's Nova software is not made by our company, Pine Research. So
we don't have any experience really.
Well, I do, but I'm not going to help you. I don't work for Metro.
Well, we also couldn't show you, right? We don't have
correct.
the software.
That's correct. Right. Yes. Even if I could, I wouldn't, because it's not my company.
Yeah.
But right. I know. I'm just being kind of silly here, but yeah, unfortunately I apologize, but it's not really within our ability, frankly, to show how to, do analysis with other companies' softwares. As I said, I actually did happen to use Metrum potentiostats and software, although I use the old EC Lab, not EC Lab, Nova, and they're on a newer version that that they released after I had finished graduate school, and I'm not even that good at using the new one. Just as a personal note, since they changed it, so unfortunately, we can't really help you there. I'm sorry.
Yeah. Sorry about that.
Yeah,
I'd reach out to Metrum's technical support.
Yeah, you might have to ask Metrum, unfortunately. Yeah, it's just one of those things. We're all individual companies. We all kind of have our own software, and I have a lot of experience using almost every company out there in some regard, but it's not to a certain extent you don't want me helping you.
Yeah.
I don't think Metrum would
want us.
Want someone from a different, like, I wouldn't want Metrum helping customers deal with our software.
Yeah.
I would rather them say, I have no idea, ask Pine. because
Yeah.
we do know, you know.
Yeah.
So frankly, I wouldn't want to give like bad advice, you know,
Mhm.
from that regard too. Because if I don't know how to do something, it doesn't mean that you can't do it. It just means that I don't work for
Yeah.
Metro.
Yeah.
You know, so
That's right.
that's kind of the deal. So thank you for the question. Good luck to you. Unfortunately, we can't really help you there.
Yeah.
This next question says, compared to other metal doped samples, only the ruthenium or iridium doped sample exhibits a high ECSA value. Where does this high ECSA value come from? We attempted copper under potential deposition, but were unable to reach a conclusion. I mean, it's hard to answer that question without knowing more about
Yeah.
your
About the
catalyst.
system and the sample
I mean,
and
that
all that stuff.
there's like couple of possibilities. I could just say very broadly speaking. One is that you did a better job doping those ones than other materials,
Mhm.
or the material you're doping it accepts ruthenium and iridium perhaps like better. You know what I mean? You know, like not every material dopes the same, uh, so to speak. Like if you try to whatever the process, whether it's a sputtering
Mhm.
process or electrochemical process or a atomic layer deposition, whatever the processes that you're adding a dopant, whatever your substrate is, um, it might bond well, so to speak, with a ruthenium dopant and an iridium dopant, and maybe the reason your ECSA was low is because the whatever other you tried palladium and you tried whatever, maybe it didn't adhere well or something of that nature. That could be one reason. The only way to sort of interrogate some of that would be to do like some kind of an elemental analysis like EDX or XPS or something like that to see like, oh well, I did this dopant. Do I have ruthenium on the surface, and do I have the same amount of dopant for each of these processes? Right. It sounds like you're doing a lot of different materials, different metal dopants, and they don't all work the same. Not every element has the same binding energy and the same adhesion, so to speak, on whatever substrate you're using. So that could be the answer. The other could be, if let's say in a perfect world, you have exactly 5% doping on all, they're all perfectly the same doped. What you've said isn't particularly surprising, although I suppose I'd have to see like, compared to what, like if you're comparing it with like platinum and palladium, that might be surprising because like, platinum and palladium are generally pretty also high performing catalysts. But if you're saying something like ruthenium and iridium are performing better than like, nickel and manganese or something, like I wouldn't necessarily be surprised. Like, ruthenium is a noble metal. Ruthenium is quite a nice electrocatalyst in a lot of cases. It performs very well. It's a pretty electroactive. It's usually used in a doping capacity because like pure ruthenium isn't really workable the way other metals are. But people use like ruthenium palladium or ruthenium platinum, or as you are ruthenium doped. From that perspective, I'm not surprised you're getting a good ECSA with ruthenium or iridium. They're great electrocatalysts. So those are the two things that come to mind. But again, I don't know that I can speak too much more specifically without knowing more details about all of your experimental process, I guess I'd say.
Yeah. I'm also wondering, are you using a technique like hydrogen adsorption to determine the ECSA?
Right. What is
Be-
your method? That makes sense.
Yeah, it's like what method are you using? Because it's possible that like hydrogen has a natural affinity for ruthenium and iridium, but not so much with copper. So that's another, like you could be depositing the same amount of copper, but it's just not, doesn't have a high affinity uh for bonding, for hydrogen bonding, or formation of hydrides as you would with ruthenium and iridium, that lend itself to giving you very high ECSA values. Plus, not to mention, it's the electrochemically active surface area. So it's also based on the active sites that are available to do electrochemistry. And it may be the case that ruthenium and iridium are just more electrochemically active when you have a surface of these things, or a surface that's full of them as opposed to copper. That's also possible.
Yeah. Yeah, a lot of transition metal oxides, copper,
Mhm.
nickel, manganese, cobalt, what have you. A lot of times, and I could speak to this because I was part of my initial parts of my PhD research project. A lot of people are looking at those not because they are great electrocatalysts, frankly, but because they're cheaper and more abundant. Platinum, palladium, ruthenium, iridium. These are, I think iridium is noble metal. I think so, but ruthenium, platinum, and palladium for sure, and gold, are noble metals, and they're also quite expensive, obviously, right? So, there's incentive to try to replace them if we can for cost reasons and things like that. So people look at, can I use other metals? But naturally, they don't work as well, obviously, right? That's the trade-off. So, from that perspective, just like you said, it's not surprising if you're finding other transition metals aren't behaving as well or have as high of an ECSA. It's not surprising.
Yeah.
So
hopefully that's helpful.
Yeah.
Let us know if you have any further questions or clarifications about that.
Should I get to this GCD question, I think?
Yeah, sure, absolutely.
So we had a million questions that we saved from, I think, the end of the last, or maybe in the last two live streams. And I do see there's a question, but I'll get to this one, then we can get to the next question here. So this was a person who asked, again, I think it was last week, hey, it flipped. Or was that just because it's a saved question?
Oh, yeah. That's because it's probably coming from the saved.
I like the name on top. I don't know why it
I know.
that way.
Anyway, too.
It's
Ask them about that.
I don't know what it's supposed to be. I looked in the theme. It didn't give us any options.
Oh, yeah.
I there's no flip kind of thing. Anyway, we're getting sidetracked here. But this person anyway had asked a very relatively simple question. It says how to calculate the IR drop in GC, galvanostatic charge discharge. So I'll talk about this for just a little bit, and I'll kind of talk through GCD and then where the IR drop kind of shows up. So galvanostatic charge discharge, commonly used with batteries or supercapacitors for as the name suggests, charging and discharging. So normally what you're plotting is voltage or potential for non-battery people, and we'll say capacity, which is just charge or time. So there's ways to look at this, but when we're charging something up, we usually have limits here. So we have a lower limit and we have an upper limit. Okay, voltage limits here. And so when we're charging, I'll use a blue color for that. We'll say we're starting at the lower limit, and we usually have some kind of a plateau, and then it hits the upper limit. Okay, and then if we're discharging, we're starting at the upper limit, and we'll discharge, and we'll hit a plateau there, and then it will hit the lower limit. Okay, this is a typical kind of charge discharge platform profiles. Excuse me, that you'll see. The red is discharge. All right. So the question is about IR drop. Okay. Well, first we have to talk about what is galvanostatic charge discharge, right? Galvanostatic charge discharge. It's the same thing as saying constant current. That's what this is. So we're applying I equals, but I'll just put a number for the sake of argument, right? So 10 milliamps, we're applying a set current for some amount of time until the voltage reaches its limit. Okay. So if we're thinking about the IR drop, right? Well, it's in the name, right? IR, I times R. I times R is equal to V, right? This is Ohm's law, right? Hopefully this is kind of obvious to you, but maybe sometimes we think about IR drop or IR compensation and we use the name and we don't think about it as an equation. This is just Ohm's law, right? So IR drop is effectively the voltage we're losing because of the internal resistance of the battery. Now, thankfully, batteries have, in particular, and supercapacitors to a certain extent, low resistance. So R is pretty small. Unfortunately, we use big current. So IR drop, the amount of ohms, this is in ohms of resistance. So the amount of volts or millivolts that we're losing because of our IR drop can be large if our current is large. Okay. If our current is not large and our resistance is low, then maybe it doesn't matter. But you can imagine if I'm charging or discharging really, really fast with a big current, like 10 minutes, zip it up, zip it, like fast charging of your phone, for instance. You want to have your phone charged in 25 minutes. Well, it takes a lot of current to do that, right? What it means on the charge, for example, is that there will be, if this, let's say, for example, this blue curve is like ideal. The IR drop is going to cause me to have a discrepancy at all times between the observed voltage and the actual voltage. So you can think about the IR drop as something like this, where this distance kind of will be lost because of my IR drop at all times when I'm charging it up. I'm going this way. And similarly on the discharge, you could think about it as being, it's going to cause my voltage to be like lower than it should be for the whole thing. So something like this. So that's kind of where the IR drop is going to show itself for the discharge and for the charge. Now, practically, what does that mean? Well, practically, it means that when the dotted lines here, the dotted blue and red lines, I know there's a lot of scribbles on the screen here, but the dotted lines, that's what you're going to see in your battery software. That's what you're actually going to see. You're going to see it hit here, but it should have hit over here. Like I'm basically being told that I hit my lower limit or my upper limit too soon, because the IR drop is telling me I'm at here like 4.2 volts. But if I times R is 100 millivolts, what's the actual voltage of my battery? It's 4.1, right? I'm losing 100 millivolts, so I can't even get to the upper limit. That's like the problem of it. And again, if I charge 10 times faster, I'm losing 10 times the voltage. So the faster, this is another reason why fast charging can be kind of harmful for batteries, because you don't actually get to the final voltage. Because if I times R is 100, millivolts, then I'm actually only at 4.1. If I times R is 500 millivolts, well, when I think I'm at 4.2, what am I actually at? I'm at 3.7 volts. So it's like, am I even getting the battery to the upper limit? I'm not, because I'm losing a lot of voltage from the IR drop. So this is why charging fast can be really problematic. And then finally, the last thing I'll say is that, the question was, how do I measure it? Well, measuring it is actually quite simple. For the most part, we just do something like impedance. We measure the R, and then whatever the current you're choosing, whatever the C rate is in terms of batteries, but whatever the charge rate is, then I just do that calculation. Like it's just simple mathematics. It's just multiplication. So if I do impedance and I get, R is equal to like 0.1 ohms or something like that. Yeah, that might be about a battery, 100 milliohms or something like that. It might be lower. Then, okay, what's my IR drop? Okay, well, if I'm doing charging at 1 amp, whatever C rate that happens to be for my battery. So IR this is very simple, right? It's 100 millivolts. 1 amp times 0.1 ohms is 0.1 volts or 100 millivolts. So then I would be able to measure that, roughly speaking, I'm losing 100 millivolts. And it could make you say, well, I don't want to lose that much. I'm going to charge it more slowly. I'm going to charge 0.1 amps. So I'm only losing 10 millivolts, and that's more reasonable. So that's kind of a rundown of the IR drop in a GCD. It's aimed at a battery because that's my field more, but there's a similar phenomenon if you're doing supercapacitors. So
nice. Hopefully he'll see that question in the future, or if he asks us about it, we'll point it to him.
Yeah.
So next question, again, while performing IT curves and chronopotentiometry for my electrocatalyst for OER, I observed an initial decay in the current, I versus T, and initial increase in potential in CP. Is it just activation? I think there's I don't know, but there's a little bit of like clarification, because normally, like if you're doing an IT curve, you're doing like a
That's
chronoamperometry
yeah, I was gonna say
experiment.
that's chronoamperometry, I guess.
Yeah, and if you're doing chronopotentiometry, you'd be measuring the potential as a function of time. But you do say that you see an initial increase in the potential in CP. So maybe you're doing both techniques.
Probably
Is
like
what I'm
separately, I'm
guessing.
guessing.
Yeah,
Yeah,
maybe you're
something
doing
like
them
that.
separately. But if you are, in a typical chronoamperogram, and let's share screen so you guys can kind of see. In a typical chronoamperogram, you're going to get something like this. So there's a couple things to note. So you have your current, you have your time, and the applied potential may be something like this. So this is time, and this is potential, or E. So you're starting at one potential, and then you step the potential up to your desired voltage. And generally speaking, when you get this initial step in the potential, the current goes like this. It has this huge spike up, followed by a gradual decay. And this fits what's called the Cottrell equation. So that's the case where, like, okay, I set the potential, I'm measuring the current versus time, and I see an initial spike, not an initial decay in the current, followed by a gradual decay. Now, alternatively, if you're doing, say, a reduction reaction, then this is flipped. So it's like, oh, you're starting your your E is here, and then you step down. maybe not that far. But you step the potential down, and now you're here. In that case, if your current was at a certain level, maybe it was at 0, it might go down, right? So it might, instead of it going down like that, it would just like boom, it would go down like that, and then slowly start to increase, right? So I want to get a little bit of clarification about that, because the only difference between these two things is whether you're doing oxidation or a reduction reaction. So when I hear things like, oh, the current slowly starts to increase after I've stepped the potential in the I versus T curve, this is what I'm imagining, which is the same thing as this. It's just instead of calling it a decay, we just call it like, oh, it's a spike up or a spike down followed by decay, as the current increases or the current decreases. And if that's the case, then this is a very normal phenomenon based on the Cottrell equation, which is this guy here, which just states that the current for a diffusion controlled single electron reversible process, homogeneous electron transfer, is equal to a bunch of stuff divided by 1 over the square root of t, or has a 1 over the square root of t dependence. So you'll often find that this kind of graph decays, the current decays with 1 over the square root of t. And if you plot this versus 1 over the square root of t, you'll get a straight line. Same thing in this case. In looking at chronopotentiometry, where you set a constant current and then you measure the potential, you can get slightly different types of looking data. But generally speaking, the Sand equation describes basically most of the response for a chronopotentiometry experiment, where the potential, the difference between E and, in this case, E to the tau over 4, is it's relatively linear. But then all of a sudden, at these limits, where I guess you've given it enough time, it starts to go way up or way down. So again, for a theoretical Nernstian process. So, oh yeah, okay. So he's just clarifying. Yes, both techniques were measured separately. Yes, and then he's saying, I applied a chronoamperogram at a fixed potential for electrocatalytic stability at the onset potential of OER and observed an initial decay in the current. After that, it becomes constant.
Just sounds like typical Cottrell response.
Yeah, I
Maybe,
think that sounds normal.
you might have been establishing some surface condition, and then the current kind of levels out where it's going to be. I don't know.
Yeah,
Sounds like all that sounds reasonable to me.
yeah, and as I said, the current response usually is like a some kind of spike, either top or bottom, but then it decays either up or down. So when we think about decay, it's like, okay, it's decaying this way, or maybe it's decaying up, depending on if you're doing an oxidation or reduction reaction. So um, I don't see any issues with that. I might also recommend, though, that when you're doing chronoamperometry, you should set the potential. Let's see, it's like at the onset potential. So if you set the potential for your chronoamperometry experiment at the onset potential, you're probably not going to get that much signal.
You might want to go more than that.
You might want to go more. So for example, if I go here and let's see. So let's do like a CV, right? Because you did some kind of cyclic voltammetry experiment. Thinking about chronoamperometry again. So voltage, current, and then let's say
you're saying voltage.
Oh well, yeah. You know
the
what?
Battery is infecting you.
I can't.
I shouldn't have said anything.
Yeah. Just keep it that way.
Yeah.
Potential. Bam. There we go.
Fine.
Cannot be. No, but if you're if you're saying like, oh, this is where the onset potential is, and that's where that's the E1 that I'm using to kind of step the potential. You're probably not going to see very much. You're going to get very little current. Even if you pick the peak current here, let's call that E2. That's also not the best potential if you want to do chronoamperometry of this experiment. You want to pick something like, here. You want something that's like 120 millivolts at least, like more positive of the E naught.
Yeah, I think 120 is the number that makes it 99% irreversible.
Yeah, it's like 99 to 1 or something
like that,
in favor. And again, this goes back to the Nernst equation, where you're able to selectively like prefer one reaction, either the reduced species or the other species, the oxidized species, because when this is like 100 to 1 or 1 over 100, it's like, okay, you end up getting a significant. It ends up being something like 120 millivolts or so away from the E naught. So your applied potential, favors this ratio in a 100 to 1 or 1 to 100 ratio. So that's where the 120 millivolts comes from. So that's my only thing about where you pick the fixed potential in chronoamperometry, that you pick it not just at the onset potential, but at a potential more positive than that, or negative, depending on the reaction.
Yep. This next question is really somewhat non-specific. So it says, will titanium and zirconium show good electrocatalytic activity or electrochemical activity? For what? Depends on what you're studying. First of all, zirconium commonly exists as an oxide. Zirconium metal is a conductor, but zirconium commonly is found as zirconium dioxide, which is not a conductor. It's an insulator. So zirconium dioxide, will not show good electrocatalytic activity because it doesn't conduct electrons. It's not a catalyst. It's commonly used as ceramic. It's another kind of aluminum oxide and zirconium oxide are used as ceramic materials because they're insulating. Titanium is also commonly not found as much as in its pure form. I mean, it's a conductive metal as well, but commonly titanium dioxide is found and used. Titanium dioxide is not an insulator, but it's a semiconductor. So there's some uses for it electrochemically, and it has some electrocatalytic activity, but it just depends on what you're talking about. Like, and I'm not going to sit here and pretend I know, well, titanium dioxide, how well does it do OER or HER or ORR or, the ferrocene reaction? Like, I don't know
Yeah.
precisely. You could find that in the literature, or you could do the test yourself. But certainly titanium and titanium dioxide can be used in electrochemical applications, either as conductors or semiconductors. For just like any catalyst, to a certain extent, they work well for some things, and maybe for other things they don't. And that's hopefully that's just kind of an overview for you, I guess. I don't know a lot about zirconium as a metal. I used zirconium dioxide when I was in graduate school a good amount. It's, like I said, it's an insulator, so it doesn't really do much electrochemically, especially at room temperature. At high temperatures, zirconium will conduct, but only really, really hot, like 600 C or 700 C or something. So at room temperature, zirconium dioxide is, well, it's useless in electrochemistry mostly. So.
Oh yeah, but just it needs to be very high temperature for it to
conduct at
useful.
all.
Yeah,
Exactly.
Yeah, yeah, no, that's true. We have a question from LinkedIn. Shujit's asking, do you think that the transference number given by Bruce-Vincent method for high concentration electrolyte can give a true value as like for dilute solution? I know researchers consider ENMR as the best method for high concentration electrolyte, but I want to know more um, about the limitation of Bruce-Vincent method for a high concentration electrolyte, if you can explain. I know we have the Bruce-Vincent method as like a kind of a combination of chronoamperometry and EIS and calculating some resistance values. Ultimately, you're trying to get the fraction of the current of which ion is carrying the current to get the transference number. I believe at least that there is a difference between like that the Bruce-Vincent method will break down depending on the electrolyte concentration, if it's too high or too small. Maybe you have kind of intermolecular, non-idealities that play a role in the Bruce-Vincent method. But I have to think a little bit more about why it would be good or bad, or what the limitations are.
So let me look through the question and think. The Bruce-Vincent method is for high concentration. I have the paper. I'm sort of glancing through the Bruce-Vincent method paper. One of the things that appears to be relevant to the Bruce-Vincent method is that concentration gradients can cause a problem, which is to say, if you have, I would assume, a low concentration in your electrolyte, you'll end up with gradients. If you have a really high concentration, probably it's all there. You know what I mean? Like, there won't be a lot of gradient because everything's so concentrated. This is my guess. What do you? I mean, does that make sense?
Oh, well, maybe Ashas, what do you mean, like concentration? Like there will be or there won't be
So
concentration?
if there's a concentration gradient, I think that it can cause a problem. If there's a concentration gradient, like yeah, right, exactly. Like where, like at the surface, I guess, right? I'm kind of not totally positive, but
it's a gradient in the electrolyte.
I think so.
Okay. So this is like if you had very low concentrations of so if you had like this actually kind of reminds me of the Frumkin effect as well. Like when you're at very, very low concentrations of electrolyte, you can get these really weird kind of behaviors to occur because of migration effects, and even the nature of it's like because you now have an electric field that extends into the solution, it pulls ions. You end up getting these like almost a doubling effect. Like, oh, the molecule moves because it feels the migration of the electric field from the electrode, but then it gets instantly countered by the migration of solvent or of a electrolyte that then repels it, and then you get this kind of new movement, sort of say. There's a whole like Frumpkin effect that I need to like
Mm.
learn more about. But what you're saying is like, okay, at very low concentrations of electrolyte, the Bruce-Vincent method maybe doesn't work so well. So maybe at high concentrations where you're unlikely to get um, gradients in the electrolyte, you can use the Bruce-Vincent method to determine the transference number for whichever, for the ions of your electrolyte.
I'm looking through, and I might. It's possible I have that entirely backwards.
No, I'm not so sure.
Because I
Actually,
haven't
I'm
done the
looking
Bruce-Vincent method myself, but I have the paper associated with it. It seems like what one of the arguments that Bruce and Vincent were making
Mhm.
was transference number measurements were previously developed using an impedance method with 2 electrodes, and there was a small AC perturbation, but it was shown that at low frequencies, the current flowing through the cells is affected by concentration gradient near the electrodes, which gives it messed with the diffusional impedance in the complex plane. So it actually might be the exact opposite. I know I spoke a little bit too hastily here, but
Mhm.
it seems like the Bruce-Vincent method, what it's doing is it's taking this decay, because it's kind of a DC method, right? It's doing chronoamperometry and watching the decay in the current, and the decay in the current is happening because there is a concentration gradient, right? There's a diffusion layer and there's a concentration gradient.
But that has to do with the analyte in a traditional electrochemical system,
Mhm.
right? Where it's like, oh, you have ruthenium hexamine or you have ferrocene, like a millimolar, and you step the potential and you're getting a decay because you're not getting enough electron transfer diffusion of the analyte. But the determination of the transference number has to do with the electrolyte as opposed to the analyte, like the K and the Cl, right? Like how much of the current is
So I
being.
I agree. And I don't think I'm talking about an analyte at all. I think I'm just talking about the electrolyte. To
Okay.
be clear, I don't think I'm
Yeah.
talking about it because I don't believe there's anything Faradaic really going on here.
Yeah.
So look,
Yeah.
for instance, at this passage
Yeah.
in the Bruce-Vincent method. If a cell of the form blah 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 is polarized by a small constant potential difference between, so this is just step, right? Step potential. Um,
Hmm.
uh, the initial current is found to fall with time until a steady state values of, that's just the control equation. Okay, fine. In the simplest case, this fall in current is due to the establishment of a concentration gradient across the cell, which is responsible for reducing net motion of anionic species, generating EMF. In other words, the point is they're talking about, in this case, uh, a concentration gradient that is forming um,
Of
during the DC step.
the electrolyte.
I think so.
Huh.
So
So
maybe it is low concentration. I mean, maybe I had it backwards.
I may have to think about it, because even in the cell that they're forming, it's like metal and then metal something polymer host. So they
Yeah,
have a
and then
polymer in here.
I don't know.
Um, which it's like, hey man, it's your experiment. You do you.
Yeah.
And yeah, that's I guess that's the one thing I've never understood about the Bruce-Vincent method, is that you're able to figure out transference numbers that helps you understand, oh, most of the current is on the chloride, or
Right.
most of the current is on the magnesium salt, or the anion versus the cation in terms of carrying the charge. That's the important thing about figuring out the transference number. But when someone does something like chronoamperometry of just an electrolyte,
Mhm.
even if it's like 1 molar or zero point 0.1 molar, the decay that you often find is, it's not associated with an analyte. It's like some kind of like, you know double layer charging type of thing, right? Because that's what you're pulling. It's like you're
Maybe that's what they're
charging the double
referring
layer.
to as the concentration gradient. It's just that there's the double layer at the surface is
Yeah.
more concentrated than out.
Yeah.
I mean, that, like, this could be a terminology thing.
This could be a terminology thing as
And I
well.
think the tricky thing here is that it appears that they're talking about this Bruce-Vincent method is more capable of handling situations where there is a concentration gradient. How that specifically relates to the concentration of the electrolyte being high or low and whether it's good or bad seems unclear to me. It doesn't even appear in the publication, Bruce and Vincent, that they make a case for whether the concentration was really high or really low. They don't really appear to delineate that per se. They're also using, like I said, you're using these polymer electrolytes. They're using very small, perturbations, small, like 10 millivolt, whatever, pretty small steps. But they're observing a change in the current and a decay. And again, whether they're calling it a gradient, but it's just the difference in the electrolyte concentration between the surface and the bulk or what have you. They're calling that a concentration gradient. And the Bruce-Vincent method is, I suppose, more adept is their argument at handling that, because in the impedance world, we get convolutions at low frequency from diffusion and mass transport. It tends to bog everything down, which is true. If you need low frequency measurements, and then the mass transport's dominating that, right? So perhaps at a DC method, we sort of, their argument is it's not causing as much of a problem. But again, I don't know whether the concentration is high or low, or whether that matters. That appears to be not clear. I'm trying to see if they say like
I think the answer is we don't know. This is what we're thinking about.
I mean, hopefully this is somewhat helpful, just kind of talking through it with you live. Again, the thing with the Bruce-Vincent method is that I've read some of his papers and but I haven't done it physically myself, so I don't have the like personal experience. I can only talk about it in a somewhat theoretical way. And even here, it doesn't even see, they talk about this polymer electrolyte. They don't say it's not a concentration thing, because they're not even using really a liquid, like they have some solid electrolyte. So there isn't a concentration to really compare with in the main Bruce-Vincent source itself on the Bruce-Vincent method. I tried to go right to the source, so to speak, and I don't have all that information. So, I frankly am not positive how to answer that one, just as it relates to the concentration and, should it be high or low? I'm not positive. The best I could say is you do methods like NMR or other physical methods, and do the Bruce-Vincent and maybe cross-reference them and see if they're roughly in line with each other, or if they break down at different concentrations, different points in time. You might find that they correlate well in some conditions and they don't correlate well in others, and you might be able to figure out, for instance, well, at these concentrations, this method is not tracking with the other method, and figuring out which one's more accurate might be possible. So
something I gotta do more to look up about using the method. But you did say thank you. So that's good.
Hopefully that's something to help you kind of think through, I guess. Anyway, but
sorry I can't be more helpful, but no, we appreciate it. All right. While we wait, we can look at the,
if you want to do the
next one,
Nernst equation something.
It looks like last week we had a question about solving for cell potential using the Nernst equation, which is probably my favorite thing. Although I don't know if they're looking for anything more specific or more interesting. But
what's more interesting than the Nernst equation?
There's not much. It's not much more interesting than this beautiful equation here. So this is the Nernst equation, and basically, if you have a redox reaction, OX plus an electron gives you reduction. The Nernst equation says that the cell potential, or the electrode potential in this case, is equal to the standard redox potential of this reaction minus RT over NF times the natural log of the activity of the reduced species, which is the product divided by the activity of OX, the oxidized species. And most of the time, the activity, practically speaking, can be translated into the concentration, but from an experimental perspective, but it is the activity of the species. So the question is about solving the cell potential. And really the cell potential is this E right here. So if you're given a problem where it's like, oh, this is, for this reaction, determine what the cell potential is when the concentration of the reduced species and the oxidized species is, 100 to 1 or 200 to 1 or 50-50 or something like that. The main thing is you would use this, which would ideally be a literature value or something that you look up, and then you would plug in, these are all basically constants, and then you would plug in the numbers for the activities or the concentrations of the reduced and oxidized species, and then see how does your cell potential shift from the E naught based on these concentrations. So if you one example I usually like to think about, which is not like a full cell per se, but if you had a wire, like let's say you had a platinum wire, it was in some kind of solution. Why did it not use blue? Let's say it's in some kind of solution. Theoretically, if I have some red and I have some OX and I dump it into the solution, the potential, if you will, of this wire, let's say it's a platinum wire, will change. Basically, this potential, which is related to its energy, will change based on the relative ratio of these two things. So I can change the potential of my system, of my platinum wire, by adjusting the amount of the reduced and the oxidized species. So that's basically like if this is like a problem set and you had to figure out what your cell potential is, then you need to know what these concentrations are. And then you can just plug it in. This is also a constant. And then you just solve for this. Sometimes you may have problems where you don't just have one electrode. And let me kind of erase some of the stuff. Oops. Not the whole thing. I want to lasso this little V there. There we go. And then I'm going to lasso this guy here. And if I add another, if I put another electrode here, and let's say you have a voltmeter, right? And you want to know what that is, right? What's this potential? You'd have to look at what is the solution around the platinum and what's the solution around here. You'd have to look at what these two potentials are based on the relative concentration of species. If this is a reference electrode, for example, like if this was a reference and there was like silver chloride, then you'd have to figure out what's the silver chloride potential based on the chloride ion concentration, because that's what ultimately changes what the potential of the reference electrode is. And then you'd figure out what's the potential of this platinum, and then you'd subtract the two, and then you'd figure out what the cell potential is that you'd measure at this V naught or this voltmeter here. So hopefully that kind of answers the question about solving for the cell potential using the Nernst equation. All right.
Looks like there's someone said hello. I'm not sure if they're typing a question, but we can.
Oh, okay.
See if the question is forthcoming, but feel free to type it in if you have it.
Mm-hmm. Yeah.
There's another question that we had. Again, it was from, I think, last week or the week before. We kind of already answered it, in part with other answer.
Yeah.
But this person had said, what does the chronoamperometric response represent when we apply constant potential for electrocatalysis?
Mm-hmm.
I guess the only other answer that we didn't really cover is like the Cottrell equation, as far as what it represents. But you just talked shortly ago about setting a potential and the current, spikes or drops, that whole part of the live stream, I guess. So I don't know if you need to talk more about this, but it sort of seems like it's kind of covered. I don't know if you want to elaborate it anymore.
Yeah, no, I think I think the main thing is that there's the fundamental electrochemistry of like the current spike in like as an electroanalytical chemistry technique. But when you're doing electrocatalysis in a catalytic system where you're literally converting molecule A to molecule B by oxidation or reduction, in that electrocatalysis regime, you may be stirring the solution, stuff like that. You're just trying to get as much, and it's not going to be a small little electrode that where the diffusional path is very well characterized. You may have a large porous electrode. So there will be some like initial spike in the current followed by a decay, but that small decay, and usually you have somewhat of like a flat-ish line, is that the current represents the oxidation or the reduction, the electrocatalysis of generating your species. I'll just draw something very very quickly in the context of electrocatalysis, which is that if you're doing electrocatalysis, you'll often find that this, you're looking at time, and this time could be long. This could be time in like hours. All right, so it's not like a couple seconds or even a minute experiment. And then you may see that like you have a little peak, but like, oh, it's kind of like this. But you may have some noise because you're generating some bubbles. Sometimes you'll see a little spike or stuff like that. But the main goal is that like, all right, my experiment ended, and like let's say this is zero current. This is zero. Well, the area from here all the way to here, right? Like all this current is indicative of, and this is positive, let's say an oxidation reaction occurring. I'm not very good at like filling in, the thing, but this whole thing is highlighted green, right? So you have all this area, and that area, this is the challenge for electrocatalysis, is the area of kind of current versus time is equal to coulombs of charge, right? So what you can do is you can figure out how many coulombs of charge and do you have. So maybe you got, I don't know, 25 millicoulombs. And you're going to use something like, oh, I know my reaction's like a 2-electron oxidation. And, you have, so 2 electrons per mole. And then you're going to use this to kind of convert how many moles of species did you generate, right? Moles of product. So that's really the only other thing I'm going to add is like in electrocatalysis where you're doing this, all the current that you're measuring is associated. All the current can be converted and should be converted to coulombs. Those coulombs need to get converted to moles of the product. And then, of course, this value of moles is based on what product, right? So you would actually just convert this to moles based on Faraday's constant. And then based on the number of electrons required to say, convert CO2 to CO or what have you, if it's a 2-electron transfer process, then, or actually it'd be CO to CO2 because I'm talking about oxidation.
Yeah.
Then you'd have to, figure, okay, well, two electrons instead of 1 electron per mole to make the product, and then convert moles to grams based on the molar mass to figure out how much did you actually make and how efficient were you. So that's the only thing. Those are the questions that people doing catalysis are often looking at and asking to figure out how efficient their catalyst is and how well does their system work. So yeah, that is it.
Let's see. So there's a couple of questions from Razmiran Janti. I almost had it. Okay. So here's some questions that are a little technical, I suppose, in nature. So please explain the mechanism, how exactly a simple polarization happens in terms of electron transfer from potentiostat and counter electrode, where it comes from, where it goes. I mean, what exactly happens to the whole system in potentiostat? It's interesting.
Yeah, that's great.
So part of the answer is we have a video. I've done a webinar. You have more material now about how a potentiostat works. So on our YouTube channel, we have one that goes through that you made, where it's it's how a potentiostat works, and then how our compensation works. So we kind of talk about the circuitry of a potentiostat, and specifically how that kind of happens. And then I did a webinar using basically the same content. The interesting thing is he's asking. It seems like he's asking like where the current goes. Now, the short answer is that the current passes in the potentiostat between the working drive line and the counter electrode. The current goes between those two. The potential is measured between the reference and the working sense lines. We could show a diagram.
Yeah,
here.
we can show a diagram.
The interesting thing is, at least for me, I don't know if you're now newly renovated
new ideas
of how potentiostat works, which is actually not how it works, and it's actually all made up and it's all fake.
Yeah, that's right.
Oh my God. But that notwithstanding, I don't know that we have a set of diagrams that has a, like, I know it's simple, but it's almost like a line connecting counter and working drive. Like we show the current is measured through the sense resistor at the working drive, basically. But it's like, well, there must be a connection somewhere drawn between counter electrode for the current. Like, you know what I mean? Like,
oh, where's the current from the counter electrode come from?
Yeah.
Oh,
like we talk about the potential. We don't usually talk about the current at the in the materials that we've done. Maybe you have, but I haven't.
Yeah.
Like I mostly talk about the potential that you apply directly to the working electrode is what causes a potential shift between the working sense and reference. We measure that. We do the feedback loop, which is all fake apparently, but we do that, and we get the potential we're after, and the current flows.
You've become so bitter about
I'm very bitter about it. Potentiostats are a mess. They're a mess. Don't ever use one. They're terrible. No,
don't ask. Just don't ask your electrical engineer how it works, because they'll tell you something and then you'll later learn that it's actually wrong.
Right. But they were just like, well, it could work this way, but does it work this way? Well, no.
Well, no.
But you could draw it like this. Yeah, but what like wires are actually soldered to what? Well, it could be like this. It's okay.
It could be like this.
I don't know. So anyway, all I'm saying to that is to bring up that, like, if you want to show a diagram, for instance, I have this diagram, which is apparently incorrect, but this is what I have for how a potentiostat works. This is kind of the flow or the schematic, if you will, of potentiostat. In short answer, while Alex maybe finds something.
Yeah, maybe
newer.
I'm able to find something.
You asked, the counter electrode is here. You see where the CTR is. This circle is like the electrochemical cell. And so we have working at the bottom here, working drive and working sense. We have reference electrode here, and we have the counter electrode here. And so what actually happens when you have a polarization is that this high gain operational amplifier in the potentiostat is changing the potential at the counter electrode. In short, okay? It's changing the potential at the counter electrode. By changing that potential, it causes the difference between reference and working sense to be measured. That's what this electrometer does. It's measuring the difference in potential between reference and working sense. That's like the potential you're after. It's this difference. It measures it. It does a feedback loop and whatever gets the potential you're after. But that's what the potentiostat is doing. It's actually controlling the counter electrode and then measuring what the potential actually is. And then it's going to adjust until whatever it's doing to the counter electrode is resulting in the potential you asked for at any moment in time. Okay. Yeah. And then the current is what, again, it's like, well, because there's a potential difference, a current is induced. I'll stop sharing. You can show your screen.
Oh yeah. I mean, no, I think you're good.
But the current being flown was at the bottom of that diagram, and Alex can share his too. But the point is, there's a current that flows, and we measure it through a sense resistor. But I don't have the schematic that shows it like looping around to the counter, because the current is going between counter and working drive is working drive.
Yeah.
So I don't know how else to describe it, like what's actually happening in the potentiostat. If you can,
Sure. And I think let me know if I need to like zoom in.
I got rid of that
question
so you can see.
So you already described that, like, the current is flowing from the counter to the working drive, and this is where we're measuring the current. But the question is also just like, where is this current coming from? Correct.
I think, and
So
the other
that's-
part is that this current we draw in this schematic
Mhm.
is showing that it's going between those two leads, basically.
Yes.
But it's also incorrect. Like current isn't going through the electrolyte through the counterlyte. It's going through the potentiostat, which is why I think the confusion comes.
Well, okay.
I mean, current. Okay, there's electrolyte moving, so that's
Yes.
sort of current.
Yes.
But like the
Yeah.
electrons are going through the wiring of the potentiostat.
Yes.
The actual like amps, the current, so to speak, or the movement of charge that you have shown as ICTR is like electrolyte movement.
It's yes, that's right.
basically.
Yeah, and that's
So maybe we're splitting hairs here. I'm just saying.
Yeah, I know. And it's what's interesting, and this is kind of the thing, because it does feel like it's like there's reactions occurring here,
Mhm.
and there's reactions. Let's make them like blue,
Mhm.
right? It's like, and then there's reactions occurring here, like whether they're oxidation and the reduction, but like current does have to flow through.
Yes.
We know for a fact that if this was blocked for whatever reason,
You wouldn't have a system.
you wouldn't have a system and it wouldn't work.
Exactly.
So so current has to come from here. How does current come from your counter electrode is through this op amp. And the op amp, and I think maybe you already talked about it, this is a slightly different diagram, but
Because this one's correct.
because this one's a little, I'm going to call it a little bit more correct, just more correct, not actually correct.
Nothing's correct.
But the thing is, in an op amp, we don't show this, but the op amp is like powered like separately. Like this has a like it has a like a plus 15 minus 15 volt. So this is like plus 15. Oh god, wow, that was my pluses and minuses are not great here. I think it's because I'm zoomed in and I'm used to so this is like plus 15, and then this is minus 15 volts. So it doesn't matter what goes in here. It's not like this goes, like this difference has to go in and like that just gets outputted. It's like this, the output impedance on like the output voltage here on this high gain op amp, this output voltage is powered independently by power supplies to the high gain op amp. Like that's what fundamentally drives it. And in particular, the current, like where do the electrons come from? The electrons, as far as I'm concerned, they come from this capacitor. So current flows through this capacitor, basically. But what does that look like? Well, no, current doesn't just move like, oh, like the electron literally like hops through the capacitor. We know that doesn't happen in the DC world, right? What happens is if I build up charge here, let's say this is positive charge, negative charge necessarily has to come here. So that negative charge is also chasing the potential is one thing. Chasing the electrons are different.
Yeah.
But if there's charge buildup here, there's going to be some charge buildup here, and I never get it right. Like, oh, if this is negative, does this become negative? But the voltage on this capacitor, whatever the voltage of this capacitor is equal to the voltage on your counter electrode. Like these two voltages are the same, and they're powered by this op amp. And what we actually do, because this is what's called an integrator circuit, is that the current flows through this capacitor powered by the op amp, and the current, the electrons here, move to balance charge, and they move to balance charge. And that's where the electrons from the counter electrode come from. And it's not uncommon that, oh, do you have some kind of weird potentiostat issue? Probably more further down in the potentiostat circuit, there are ways that we're able to discharge this capacitor so that your counter electrode doesn't just show up charged when you hook it up to an electrochemical cell. So we do things to like discharge the system. Of course, it'll have an open circuit, but that's where the electron comes from, as far as I'm concerned. Well, then you may ask, well, where does this electron come from? Well, it's like, I don't know, man. I can't.
It just shows up.
I can't. And this is like a high level, this is a very high level question. So I don't know whether or not.
It comes from another set of circuitry that you haven't been informed exists, but definitely exists in that whole diagram is a lie.
Yeah.
That's the answer.
That's the answer.
Because like all of these things we do, we admittedly they are simplifications.
Hmm.
Because if you open up your potentiostat and look at the printed circuit board, there are a lot more resistors and op amps and capacitors and wires than that diagram shows. So somebody's lying
somewhere.
somewhere. It's quite a bit more complicated than is easy to describe.
Yeah.
And easy for us to understand, and we work at the company. So
Oh yeah.
that's a good talk through some of they ask what is actually happening to the potentiostat in the system.
Yeah, a little more understanding. I mean, and to the degree what you described, that is still very valid. I know you're it's like it's a lot. You feel like it's a lie, but it's still fundamentally
I mean, if you just say like, I mean, a potentiostat basically is like this. You can say like in the most simple possible way, a potentiostat controls the counter electrode potential and measures the resulting potential and then adjust it until it's right.
Yeah.
That's basically it. Whether you're in galvanostatic mode, potentiostatic mode, regardless of what you're measuring, whatever the stability filter is, whatever anything else, that's basically what a potentiostat's doing.
Yeah.
And then it's like you can get more specific, being like, well, actually the voltages here are here, and the current goes in this the way you drew it or whatever. There's more, but like generally speaking, it can be boiled down in the most simple terms to just that.
Yeah.
It's a device that controls the potential of a counter electrode, which then causes current to flow and a measurable potential to be generated between the sense lines.
Yeah.
That's in essence what is physically happening in the system, so to speak.
Yeah. And we create feedback circuits.
Yeah, right.
Where we create logical conditions where potentials that you tell the potentiostat to be equal to are potentials that the working and reference electrode need to be equal to.
Right. Because if we didn't have those feedback loops,
yeah,
everything I described would be just a free for all. You just say, well, just to get some potential.
It's plus 1 volt.
It's something.
Something. What?
There's some current flow and something's happening. Who cares?
Yeah.
Hope that's what you wanted.
Hope that's true.
So we have a lot of feedback loops and a lot of other things that are getting there. So Cricket Scientific.
Yeah.
Long time no see. It has been a while. Hope you're doing well. Good to see you again.
Yeah.
Thanks for being here.
Yeah, thanks for showing up.
Binny Jint has a good question. Says, when assembling an electrochemical cell where you need a clip to your working electrode, say a glassy carbon film with a tungsten clip, how do we ensure the clip doesn't participate in Faraday reactions? Is tungsten good? Tungsten's fine. Tungsten is a really nice metal. It's conductive. It's hard. It's really durable. The question isn't whether tungsten's a good metal for this. The question is about how does it not participate in the reactions. The answer is you must make sure your clip is not in solution. You must make sure that your solution doesn't wick up your cell, your electrode. And if those things are unavoidable, you must make sure you have enough insulating material somehow present to make sure that's the case. So let me draw a few things that kind of illustrate this for you. This is a common thing that happens, is that you'll have some substrate, and maybe it's a square, maybe it's a rectangle, maybe it's glassy carbon or carbon paper, and you have your catalyst on it. And it's like, okay, well, cool. I got to do an experiment. So I'm going to put this in some beaker and now it's in my solution and I have it there. And then it's like, well, how do I make electrical contact to this darn thing? And it's like, okay, well, I have to put a clip on it, right? And it's like, okay, I clip it to this alligator clip, and that goes to my potentiostat. But now my alligator clip is part of my electrode because it's in solution. And it's like, that's a frowny face. That's not going to work, right? Okay. So you have a couple of options, right? One is that some people will do something, for example, where they modify their substrate so it's like a flag. So you might have to find a way to make your glassy carbon, your carbon paper or something, have a flag of some kind. We call this a flag. I don't know what you want to call it. That's just the name to people use. But there's like an edge of it that I can then put on my clip, but it's above the solution so that when this is in solution, I can submerge my catalyst entirely, but all of this part is above and out of the solution. So that's a happy face, right? So that's one possibility. So in this case, it doesn't matter what your clip is. It could be tungsten. The two most conductive metals on Earth, I believe, are silver and copper. So people usually use silver copper epoxy or copper tape, silver tape, stuff like that, right? People use eutectic materials, whatever. It's just stuff that's really conductive because you don't want to have it add extra resistance or impedance to your potentiostat, to your cell. So something that's well clipped, has a firm grip, firm touch, doesn't destroy the substrate, whatever. But those are kind of things that people are looking to use. The other, thing you can try, of course, is that if you have your substrate, and let's say you're kind of stuck, you're sort of, well, no matter what I do, I don't have a flag. I can't make a flag. Again, maybe you can construct one, but you just have to be aware. Anything that's touching the electrolyte, if it's conductive itself, it's part of the electrode. It is. You can't avoid that. That's what electrochemistry is going to do. If it's in solution and it's touching and it's conductive, it's part of your electrode. Now, it doesn't guarantee it's going to participate in the Faradaic reaction, because maybe your tungsten clip is not electrocatalytic in whatever you're studying. Maybe it just contributes to the background current. Like, I don't know, but you don't want to have to answer that question. It's annoying. You don't have to have some accidental composite material that consists of clips. So sometimes what people do is they'll have, for example, some sort of clipping mechanism. I don't know, whatever the clip is here. Looks like a pair of pants. Okay. And then you'll get something like Teflon tape. So I don't have any, I'm just using green. I don't know what other color to use. So PTFE tape, you might see this Teflon tape. It usually comes in a spool. It's usually blue for some reason, but it's like, it comes in a little spool that looks kind of like this. And it's wrapped around. And it's
you have to like pop it out.
Yeah, you pop it out
to expose the Teflon tape.
Exactly, and it's really smooth or whatever, and it's insulating. So what you do is you just you're gonna wrap the hell out of this thing. Seriously, hard to be crude here, but you're gonna wrap every bit of this that's in. So this is like the solution, whatever. So I drew the level too high, but you're gonna wrap this in Teflon tape. And it kind of sticks on itself. So you'll have to be careful, because like if the solution can like seep underneath it, you're in trouble. So there's sometimes it's not easy. You'll have, it depends on the geometry of your electrode. It depends on a lot of stuff. But basically, if you can wrap all of the part that's submerged in electrolyte in Teflon tape, then whatever is touching the Teflon tape is insulating. So you're taking that out of the equation. It's not part of your electrode anymore, because it's not touching the solution. Again, if the solution can capillary action or wick its way, whatever the wording is, diffuse its way into the clip underneath the Teflon tape, you're in trouble. So you have to make it really tight. Sometimes you got to like wrap it really, really tight, press it down. There's people have tried all kinds of stuff. Sometimes people use Kapton tape. Kapton tape is another one. It's used for like thermocouples usually, but it's an insulating polymer tape. It's non-conductive, of course. It sticks. That it can work a little bit better in some cases. But basically, that's the other answer: is insulating the thing that's touching the clips is your other option to try to make sure that it's out of the solution. So again, my main feedback is it's not as important what the material is you're using as a clip. Tungsten, sure, it's fine, but it's about trying to make it really well insulated or out of the solution. You can't avoid it. If it's in the solution and it's conductive, it is part of your electrode, and that's not what you want, right? You're trying to measure a very specific thing on a very specific material with a specific surface area. Adding a clip into that convolutes it. It's not what you want. So you got to work on one of those methods, and hopefully that'll kind of help you there.
So the next question is, what are the biggest challenges in calculating reliable turnover frequency in electrocatalysis, especially active site determination? How can we improve it, and why are many researchers hesitant to report turnover frequency? Well, I think you've kind of hit the nail right on the head.
Because measuring active sites is really hard.
Yeah, measuring active sites is not easy. A lot of people are using it's like the methodology. Like some people will use things like CO adsorption or something like that, because like CO prevalence, but it's like,
that's an estimate.
Yeah, and that's an estimate,
Mhm.
and then it also like it poisons your catalyst, so you can't use it afterwards because you need to then determine how well did that catalyst perform over time.
Right.
So I think people feel like the determination of the number of active sites and that inaccuracy
Yeah.
is the fear in trying to, in being hesitant to report the turnover
And I feel
frequency.
like you see things, for example, because the turnover frequency is sort of unitless. Well, it's like per
Yeah.
time, right? So
Hmm.
it's like moles of product over moles of active site. So those moles cancel, and then it's per second or per minute or
Yeah.
whatever.
Hmm.
But you'll see things like I got moles of product per milligram of catalyst. Because like that's something that doesn't require you to poison your catalyst to determine, and then you can't
Yeah.
use it, and it's like a catch-22. You're sort of stuck. If you just do it by certain, you can know things about your catalyst that are easier to measure, like the number of milligrams of it, right? The surface area in some cases you could do BET,
Hmm.
get the specific
Yeah.
meter squared per gram. Okay, like there are things you can learn about your catalyst that are easier than active site. And so people might choose to report it that way. Well, our turnover frequency, so to speak, was, X moles per milligram of catalyst per minute or whatever. But it's exactly that. You're right. You kind of self-identified with your question, and
Hmm.
it's a smart observation.
Yeah.
It's just really weird and tricky to have accurate measurement of the number or the moles, whatever you want to call it, right, of
Yeah.
active sites. It's like, man, that's a hard thing to measure. So how can we be sure about our turnover frequency unless we happen to have a way to really well, like, know that quantity,
Yeah. And that's also there's also a small caveat should mention, which is that determining the number of active sites for a heterogeneous catalyst is in a way sometimes harder than figuring out what's the turnover frequency for a homogeneous electrocatalyst, right? So in one case you're looking at, like, I have a surface and there's only certain spots on my surface where the catalysis will occur. But in a homogeneous catalyst it's a bit easier because it's like, well, I just add a certain amount. Like I know the moles of the catalyst that I've provided, and I know the moles of the of how much substrate I've added, and I can just keep running it until, like, well, it kind of dies. So I can assume, oh, 1 mole of my homogeneous catalyst can produce a 300 or something, can turn over 300 times or 500 times to convert the catalyst over, because it's an easy, like, moles to moles kind of situation.
Mm.
But most people are dealing with heterogeneous catalysis instead of homogeneous catalysis, so I should also mention that.
I always screw up heterogeneous versus homogeneous. It always makes in my head electron transfer. It's not an engineering thing because it's not concerned with just a random number that correlates with something.
And hence
Or
it is difficult.
yeah, and it's not just some like exponent that happens to make things work.
Yeah.
So I'm out. I got nothing. I'm an engineer. I'm like, tell me how to make it work.
Yeah.
Don't tell me why. I don't care.
As the phase angle increases, the propensity for the battery to explode,
Yeah.
increases.
What else do you need? I don't know
It's
what the
just like,
problem is. Who cares?
why?
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 I don't
I
know.
don't know.
Who cares?
Who
I
cares?
saved your battery from exploding. What do you
Yeah.
care?
Yeah. What do you care?
I don't care. I don't have to know why. That's not my job.
Yeah.
I just have to make it work for you. That's
Yeah.
all
Where is the electron exactly coming from in the counter electrode?
There's only one electron in the world. It moves around
And it moves around.
at the speed of light.
We're chasing that electron.
That one
all
electron.
the time.
That's right. I need to borrow it for a bit after this, if you don't mind.
Borrow
the electron. Then you can have it later tonight. I have some work to do. So
How long will you need it?
a couple
Because
hours.
it'll hopefully get back to me pretty quickly.
It will. Once I'm done with it, like it's with you instantly.
It'll
'Cause
be
the speed
with
of
me
light is pretty
instantly.
fast.
Yeah,
but,
that's
you
right.
know.
Well, Cricket Scientific has some comments, questions. Just basically, hello, good to see us. I've been studying things on my own. Happy to see you guys again.
It
Also
is
happy
good to see
you
us. That's
too.
true.
Yeah. I have a small doubt. Is there any resources that address the mathematics behind electrochemistry? I have seen a lot of governing equations involve deep math applications, The reasoning is extremely important, I believe. My mentor keeps telling me that everything that we do in electrochemistry has a reason, and I believe it can be extended to all of science.
Man, this is deep.
This is deep. Some resource that address things deeply apart from Bard and Faulkner would be nice. Well, that's fine, because if you want to get deep into the math behind things, it's like Bard and Faulkner is
Yeah, I
the
was
way
gonna
to
say,
go.
how much deeper do you need? There's a lot of derivations of Bard and Faulkner.
Yeah.
I don't know what like level of depth you're concerned with here.
Yeah, and then there's also the reasoning behind certain things. So it's so I get that. I feel like that from my perspective, I think that there's two things. There's the math, which is just like, okay, I put this number and I plug these numbers in and I do a Laplace transform. I take this integral and then I get a number or something. And then there's the reasoning behind it. Like, what's the thought process behind it? Like, in terms of the model, right? Like,
Yeah.
And I think to a certain degree, you can in some ways separate those two things. Let's take I'm trying to think, like one thing that constantly we always talk about is like the the diffusion. The current response for a diffusion controlled thing has a 1/square root of time dependence.
Mm.
But the charging of the electrical double layer, a non-Faradaic process, has a linear time response, or 1/time response. It has a linear relationship to like the scan rate in, say, a CV experiment, but the peak current, for example, has a 1/square root dependence. So that's math. That's just like a math thing. But can we intrinsically think about like, well, why does one thing have a square root dependence and why does one thing have a linear dependence? Fundamentally reasoning, like what's the fundamental reasoning behind those things? And that doesn't have as much to do with like the derivation of some of the equations. They're more like interesting observations in life, why things are linear versus non-linear. And I'm not going to tell you like why one's linear and one's non-linear, but we can think about conceptually, uh, is something, if something is easier or something takes time, that process ends up being a 1/square root of time depends. And actually, if you look at the math behind some of those derivations, some of those math derivations ultimately come into solving these like error functions. And when you solve the error function, you get this square root dependence or something like that. And we see it in real life. But then we can ascribe or attribute like a physical phenomenon, like diffusion is the reason why you have 1/square root of time. And like double layer charging is like, it's just based on how a capacitor works. That's why it has a linear response. And that's just equal to like the charge on a capacitor has a linear relationship with voltage, but that's not the case with Faradaic processes, because actually the nature of how the molecules move is different. One's diffusion controlled and one is just, it just shows up. So
It's just there.
it just shows up. Yeah. So I don't know, cricket scientific. That's kind of a little bit of my thoughts. I don't know.
Despite being an engineer and often taking the approach of, I don't care why it happens, just give me an equation that helps work. I actually find myself stuck in the wanting to know why something happens.
Why something happens.
One example that I would use, for instance, is my impedance webinars. I define, and I've shown the mathematics for how to calculate the basically you're solving these expressions for sine waves, right, in and out. And the explanation, in short, for why do we have imaginary impedance as one of the variables of an impedance experiment is just math. It's because when you put a sine wave in and you have a sine wave out and they have different arguments, simplification of their quotient involves complex numbers. Everything I just said is mathematics. It's not why, right? It's like getting down to a why I often find myself trying to think about a good way to explain things because I like using like stories and real like analogies the way similar
Yeah.
to you, we have that in
Hmm.
common. Like I like I always try to use analogies like the music analogy or the elephant and the blind
Yeah.
man and the elephant. Like these are things that I've used in my webinars and in describing these processes because I just think as human beings, your question is good, Cricket, because it's like this is how we think as human beings. At least some of us do. Some of us aren't maybe human, but the way we think about things is to try to relate them to things that we understand, and stories and analogies and things of that nature help us conceptualize stuff. So to your sort of deep point about like extended to all of science, like there's a reason behind why we have these things and why. And it's like sometimes the hardest thing for me in my understanding and in my frankly my job, because I'm teaching
Yeah.
these things, I'm giving webinars, we're writing support articles, we're just doing these different things and collectively learning. Like Alex and I are PhDs in
Yeah.
electrochemistry for a decade, but we're still learning all the time stuff, and I'm still confused about how potentiostat works. But like in doing so, I often find myself as well asking myself that question, not just for my own edification, but also because I'm like, well, how am I going to teach someone this if I don't understand it? If I can't understand why this is happening, why do we get imaginary numbers? Why is there a 1/square root dependence? That's why we come up with things like, your Warburg video where you describe like there's a time element and a distance element. And so that's a way to kind of conceptualize why there's, things are moving in time at a certain rate. And if they're moving more slowly than expected or more quickly than expected, it describes this process. And a Warburg is kind of when they're moving in a perfect plane. Like there's
Yeah.
some of those are like a really cool way to describe it. But I think my main point to you, Cricket, is just that like in some sense, there isn't a better answer than math is the answer. Like mathematics and the derivation leads you to these observations. And what is science if not for definitionally a way to describe the things that we see around us? That is like the definition of the word science. It is human beings' attempt to describe the world that we are observing. That's it, right?
Mhm.
And sometimes we find ourselves with helpful analogies that allow us to gain some insight and describe them in ways that are more understandable. And sometimes we're stuck with when we observe this phenomenon and we apply these expressions to them, we get this mathematical equation. And that's the explanation. Math is sometimes the answer. And that's unsatisfying in some ways because it's like not something you can put a picture on, it's just numbers and letters. So I get why it can be tricky for sure.
Yeah.
Um,
I put just very quickly, I put another book. One thing that might help you.
is that straight out of Compton?
Yeah, this is straight out of Compton. This is Understanding Voltammetry, second edition is a book. So like Bard and Faulkner goes through the math and all those things. I have actually found so reading other books will also help kind of broaden your understanding of things. Like it won't like your understanding of things won't just come from one source.
Yeah. It'll come
You'll
over
learn a
time
lot more
too.
stuff. Yeah, from other sources. And I have found that book in particular, Understanding Voltammetry, second edition. There's a third edition. I don't know how good it is or how different it is.
Mm.
But I find Understanding Voltammetry like, oh, Bard and Faulkner will have a very like concrete explanation of like what the rate constant is for electron transfer. But in Understanding Voltammetry, they actually describe like, well, why do some molecules have a fast electron transfer rate constant and some have a slow electron transfer rate constant? It's like, oh, that's kind of interesting. And then there's maybe even a little bit of history is important. So I like that book too in concert. It's a lot easier of a read in terms of just like the density of stuff, but there are also just some very good explanations to things in that book. So that's another thing I wanted to
And this
share
is
with you
also
that would be
true. In
helpful.
some cases, you just have to accept math. Sometimes you just need to accept that math is the answer. Why does this do this? Why does this derive this way? It's like
Hmm.
we have some analogies, and that's what I try to do in all my webinars and our YouTube videos. And
Yeah.
when these questions, if there's an analogy that I know or a way to conceptualize it better, I share that. And then sometimes the answer is just, I'm sorry, I don't have a better answer for you. It's just math. That's it. It's just math. It's like there's reasons why we use the mathematical expressions.
Mhm.
For example, you'll have boundary conditions, and you'll have the
Yeah.
mathematics behind the signal you're adding. That's a real thing. It's
Mhm.
a signal you're adding and use the math, but the solution is a partial differential equation, and the solution is just this. This is the answer. I don't know what to tell you. Like a bunch of mathematicians 500 years ago just sat down and were like, I
Uh,
figured it out. If
yeah.
I use an error function or a Bessel function or whatever, I can solve this differential equation. That's the answer. It's like, oh, cool. It works. When you plug it in, you take the derivative. It's correct. Like that's the answer. So it's like there's no other. I don't have anything else to tell you. You know what I mean? Like there's nothing else to say
Well,
in some of those cases.
I am going to say that like there is still there is also I think it's harder, but like there are also some like the reasons, right? Like there's ultimately like so whenever you're publishing like a chemistry paper, it's always like, hey, you got all this data, you got spectroscopy data, you got echem data, you got like imaging data. Like you always it always has to be about what chemically is happening. Like chemists always like every chemistry paper, if it's a good paper, should
Mhm.
should be describing some interesting chemical bonding, non-bonding reaction that's occurring. Like that's the answer to a chemistry paper. Every chemistry paper needs to talk about like it's not just we detected this thing, it's like the bonding or the receptive sites for this thing have an affinity for it that helps you that helps it bond to this particular thing. So there is a reason. I always think it's hard, like it's hard to get it even like in taking differential equations and you find like, oh, the general solution to this differential equation is this. But like that's the model for like, I don't know, when I was taking the class, it was like the predator prey model or something with
Mm.
like wolves and rabbits or something with like wolf and rabbit populations like bouncing up and down. And it's like, but you could rationalize like, oh, if there's lots and lots of rabbits all of a sudden, well, their population goes down because like there's lots of them. So the wolves have an easy time like feasting on them. But then when the population goes down, and the wolves have a harder time like finding rabbits, and then like, oh, their population goes down. Well, now there's less wolves, so now the rabbits are able to like populate and do. So it's like, okay, there's reasoning as to why there's this solution, this general solution, gives you this like this balance as you plug one number in, one thing goes up, one thing goes down, this thing goes up, this thing goes down, and you can always reason back to like, oh, like there's more wolves, there's less wolves, there's more rabbits, there's less rabbits, they're hungry, they're not hungry.
What is it with scientists and animals killing animals?
This is what my differential equations teacher
Wolves
used
eating bunnies, and
with
then
the
there's
predator prey model.
Schrodinger's cat. It's like, well,
Yeah,
the cat is alive or dead, and there's more than one way to skin a cat. It's like, why are we obsessed with torturing animals? This just seems mean.
because no one cares if we torture an electron, and we torture electrons all the time.
Then why don't we talk about the electron positron prey model or something?
Electron positron prey model.
It just seems. Why are we talking about bunnies? Are cute, man. We don't have to eat bunnies. And Schrodinger could be Schrodinger's electron. We don't talk about Schrodinger's cat. The
I
cat might be
know,
dead.
I know. You know what?
I'm a dog person. Don't get me wrong. I'm just saying.
Just saying.
It's like this just sounds so mean. Man, we're such jerks as scientists. All right. Well, I hope that was helpful, Cricket, talking through some stuff. And you sound like you're on the right track.
Yes.
And if anything, you're not, as I always say, you're not alone
Yeah.
in having to accept mathematics.
Yes.
I'm going to get to this question because this is a good one.
Yeah.
Actually, I can kind of talk through this. It says, thanks for the clarification. Another question is, during EIS of a coated metal system with no pores from two arcs, which is attributed to which interface and why? In short, probably you have two arcs. You probably have a small one and a big one. You probably have one that appears at the left on the Nyquist plot and one at the right. If so, most probably the one on the left is the interface between your substrate and film, and the one on the right is the interface between the film and the electrolyte. So probably, I'm making a lot of assumptions here. You can clarify.
Mhm.
You probably have something like this, where you have maybe two arcs, and one of them's small, one of them's big. It's usually this way. It's rare, but sometimes you have a big arc than a small arc. Your circuit is going to be a leading resistor, and then probably two RCs, right? Something like this.
Mhm.
Okay. And so probably what you're going to have, this is like ohmic resistance or uncompensated resistance. This first one here, this is going to be substrate film. Substrate film. This second, just second in order that I drew it, not necessarily second in terms of timing, but this would be, let's say, film electrolyte. Electrolytes. Okay. I'm going to call this, this one is 1 and this one is 2. Okay. And so that would be 1 and this would be 2. So that would be the most likely situation. Okay. The reason why I draw this conclusion, and you can clarify if your data doesn't look like this, but this is usually what it manifests as, arcs and by extension capacitors, and by further extension time constants, they show up on the Nyquist plot by order of their magnitude. So this, if we call this C, like C1 and then C2, okay, this is going to be C1, which is less than C2. Okay. The reason why you're going to see it this way is that the capacitance, so the capacitive element, if there is any, between the substrate and the film, which you said there's no pores, so you basically just have this interface between your substrate, you have your film, and then you have, you know, your electrolyte or whatever. So the interface here between substrate and film, this interface, I'll just draw a little arrow here, whatever. There's a capacitance associated when any two dissimilar metals are there. There's a capacitance associated with it, like some interfacial capacitance. Oh, it's the opposite.
If
big arc,
if it is a big arc and then a small arc at low frequency,
so you have the opposite. Still could be the case of what I'm talking about. I'll finish my thought, but then I'll try to tailor it to what you're talking about. Needless to say, as I said, the capacitance usually refers to the interface here, and the interfacial capacitance between two like solid materials is usually pretty small. The interfacial capacitance between a liquid and a solid here, this one, this interface, is going to be larger. There's going to be like double layer, you know, whatever. You're going to have a bigger capacitive element there. And so typically the capacitance of the second arc is going to be bigger. Now that doesn't, what you said is you have big arc then small arc. What I just described can still be the case. Okay. It just means that the resistance of the first one's bigger. So what that might mean, if you have something like this, you still have C1 is less than C2. But what it means is that R1 is greater than R2 for whatever reason. And this just could be you have poor adhesion. Like there's not much capacitance here, but there's a lot of resistance. Like maybe the film isn't sticking well to the substrate, and so there's a high resistance or high impedance there. Or maybe you just have such a good reaction because you have a really good overpotential or something that your charge, this resistance here would be like the charge transfer resistance, R2 maybe. Maybe you just have a really low charge transfer resistance. And so that resistance is small compared to the resistance of your substrate and your film. But fundamentally, you still have the capacitance is showing up here because probably the liquid interface is going to have a bigger capacitor. So that's my assumption for you. Again, not seeing your data, it's hard to exactly know with 100% accuracy, but that's kind of how these things tend to look. And thank you for clarifying. But I still think for the most part, the first interface probably is the substrate in the film. That's usually how it manifests itself most of the time.
If you haven't done so already, I mean, Neil has did webinars on this not too long ago. And if you have EIS data, you may try doing circuit fitting. And Pine Research offers really inexpensive EIS circuit fitting, and you can actually play around with, you know, building that specific model and then playing with the RC values to say like, all right, one's bigger, one's smaller, and then where does it show up in the Nyquist plot? And ultimately, like, it's generally very, and it doesn't matter what EIS data you have, you can always import it into our software. But it's very inexpensive. It's like $20 basically. And you can just kind of play around with it instead of kind of pushing numbers to just like change it, we have these slider bars that allows you to adjust the capacitance, adjust the resistance of any part of the circuit element, and watch how not only the Nyquist plot changes, but also how the Bode plot changes, because that'll also inform some of your thought process and decisions in terms of, which is it even a good fit or a good model, and what could be happening in your system.
Yeah. We're kind of reaching our time
Yes.
here. And this is probably a good also time to mention what I talked about
Yes.
a couple hours ago at the beginning. So for those who are joining us now, it tends to be the case. We get a lot of folks at the end who ask those questions. We do this every week, or when we are most of the weeks we're able to on Fridays for 2 hours. This live stream. We appreciate everybody who joins, but one of the things that tends to happen is exactly what's happening now. So as unfortunately as we hit our time limit, and a bunch of folks have questions, and we're done. Unfortunately, we can't really get to all your questions. So one of the things that first I'll show you, I was going to bring up our website. Just to Alex's point, this is the circuit fitting. You can see a monthly license is like under $20.
Yes.
If you want to do some circuit fitting and simulation with our software, you can purchase these on our website directly. Also, what I'll show you again is that you can, as many people do pretty often, is a contact form for us. Stay tuned, because soon we'll be making this, more specific to this live stream. But what we're probably going to be doing is, for those who, for let's say now you've joined and you asked a question and you're being told that we're not answering it because we're at time. You can come here to our website here and submit your feedback, or just put a question down here. And also you can see, I think in this, maybe the website feedback doesn't, you can definitely attach a file. So like technical, I think there's a file thing here. So you can attach a file, if you have a CV, you say like help with my EIS data, it's awful. Right. So you're going to do that, and you're going to attach some images, because one of the things with our live stream is, of course, we can't see your data. You're typing into
That's right.
into YouTube or LinkedIn comments, and you can kind of only give so much information. So we're going to be moving to a system where you can put your questions into our website, and you can put your YouTube name as well as your name, and tell us what university you're at, or where you're doing your research. Put your question, and what we're going to try to do moving forward is answer the questions that folks have put to our website for the first hour or so of our live stream. Yeah. Because we want to give people a chance to really ask questions and get them out. And maybe if you can't watch us live, or it's late, in the live stream like now, and perhaps you just bad luck, you haven't had a chance to get your question answered. We want to try to address that. So we're going to have some dedicated time moving forward, where we'll have questions you submit to us on our website, and we'll try to answer those with priority. And then we'll still answer live questions, and we'll have the end of the last bit of our live streams for that as well. But I want to encourage you to use our website, pineresearch.com. Go submit your questions there. We will soon have an interface specific for YouTube. But for now, I just want to encourage everybody to do that, and we'll try to give some priority to folks who are willing to ask their question there, so we can really get to them in a thought out way.
Yes. Yeah.
So
yeah, I agree.
So stay tuned for that. We'll have more on our website, really probably specific to YouTube, ask us anything, directing you in that way. But for now, that's we're going to call it a week, I guess.
Yeah. Yeah.
So,
I think we're both here next week.
Should be.
So yeah, we'll hope to see you next week then.
Yeah, perfect. And hope everybody has a great weekend. Maybe it's already weekend because, well, most of Asia's in Saturday.
That's
already.
right.
Crazy.
Yeah.
But
right. In the future.
Exactly. They're futuristic. So anyway, thank you, everybody. We appreciate it as always, and we'll see everybody next week. Take care.
Bye.